Okay, good afternoon, good morning, good evening, depends on where you are in the world. So we are here today to have a new CASS talk, this time with Professor Sandro Binsfeld Ferreira from Unisinos, Brazil. We have also the pleasure to have Professor Bumpy that will be the session chair today. So now I give the floor to Professor Sérgio Bumpy to start sharing the session. So thank you again, Sandro Ferreira, for accepting our invitation, and also Sérgio Bumpy to accept our invitation to be the session chair today. So the floor is with you, Bumpy.
Okay. Thanks, Sandro, for volunteering to present this talk for the CASS Sequence System chapter of Sul. Sandro is a good friend whom I know for the last 12 years. He's currently an associate professor at the Unisinos University in São Leopoldo. He's also a researcher at the ITT CHIP, which is the Institute for Semiconductor Research in the same university. Sandro graduated from a very prestigious engineering school, the ITA, Technology Institute of Aeronautics in São José dos Campos in '92. Then he came to the south of Brazil and he took a master's degree at the Pontifical Catholic University in Porto Alegre in 2005. And then around 2009, I think 2010, I met him at the Federal University of Rio Grande do Sul, where he worked from 2009 to 2014. He was an instructor, a design professor for the RFIC of the IC Brazil program. Okay, so he provided, tutoring, mentoring, and design for the students in IC Brazil who were specialized in RF. RF has been his field in the systems area, so his research interests are in the wireless communications in general and on systems, but also since joining the IC Brazil program in 2008, I think, he became dedicated to the RF IC design, and that's the field he will finish. He finished the PhD in 2016 in joint work between the Federal University of Rio Grande do Sul and Delft University, where he spent 2014, 2015 in Delft University of Technology in Netherlands. And he, over the years, has developed many interesting circuits in discrete-time receivers. That's the topic he'll be addressing today. So discrete-time receiver basically, presents several issues and advantages that he'll be explaining to you. And those are very relevant for low power RF, okay, which is in general the trend for, let's say, state-of-the-art research is reducing the power consumed by RF. So it's a pleasure for the chapter to host his talk. He's also a member of the board. We founded, Sandro, myself, and 20 other people in Rio Grande do Sul. We founded the solid-state circuits chapter of the south of Brazil, not only Rio Grande do Sul, but these three states, Santa Catarina, Rio Grande do Sul, and Paraná, which is a chapter devoted to the solid-state circuit, integrated circuit design and development. So the floor is yours, Sandro. Thank you very much for volunteering to present this very interesting topic, which is certainly most of you will enjoy. And thanks again for being such a let's say, reliable and continuous volunteer with the IEEE activities here in Region 9. Thanks. Have a nice talk.
Thank you very much, Professor Bumpy. To me, it's an honor to be here presenting at this very prestigious chapter, and also to have been introduced by you. It's also very nice because Professor Bumpy is one of the folks that brought me into the microelectronics after his first classes that I have attended on microelectronics with him. So it's really a pleasure to be here. Today we'll be talking about discrete time receivers for IoT. Actually, we have some part of this work is related to this paper here, and the outline of this presentation. I will stay a long time talking about what is a discrete time receiver and helping to understand its basics and its advantages, so that we can see a real implementation with very nice, very good performance in terms of BLE, Bluetooth Low Energy, and then we will see what are the differences from a traditional analog RF receiver design. So, of course, we are all talking about IoT and 5G and all this connectivity that we have with person-centric sensor networks, connected cars, smart homes, sensors everywhere. And behind this, we have connectivity and a struggle to reduce power consumption and integration. Those are the main points to make this possible. And the standards that are dominating this advances at this moment are more related to Bluetooth Low Energy, to NB-IoT, also with a little bit of Zigbee Alliance, and recently with LoRa technologies as well. So talking a little bit about the Bluetooth Low Energy, which is one of the important technologies, right? We can see here at this chart the main works over the last few years in terms of performance. We have sensitivity here, and the standard defines that the sensitivity should be below -70. Of course, you cannot sell a chip with -70 dBm of sensitivity. We have to go lower. And here we have the state of the art right at the bottom at about -95 dBm of sensitivity. And we can see here, if we look at the legend here, in orange, we have the discrete time receivers, which are not very much. We don't have many. It's kind of a new architecture. But we still have a very good performance with these receivers, and very good power consumption as well, right? And we can also see here that some of these designs have off-chip components, while the others have only don't have off-chip components. I mean, switches and filters are all integrated in the receiver. So actually, the design that we'll be presenting is here and here. So initially, why discrete time? So actually benefits from technology scaling, because when we advance the technology, we reduce the VDD, the supply of the blocks, and well, the threshold voltage doesn't reduce so much, so it makes it hard for many analog architectures to work with this. But we are using basically digital intensive building blocks. We are working with switches, inverters, and clock generation, and all of them benefit from this scaling, right? So it is very adequate to newer technologies. Here I have one example of a discrete time receiver, which was published in 2004. It was actually a commercial receiver, and we can see here many blocks that are not really common in the analog RF design. We can see, for instance, a sampler, a sync filter, decimation, which is typically digital, and infinite impulse response filter. And this happens in this receiver to provide a low IF architecture. This work, which was done in 2017, shows clearly how it works in terms of signal processing, right? We can see here that we have the LNTA receiving the signal from the antenna. We have to change it into current so that we can switch the current using this sampling mixer. And when we go to the switched capacitor filters, which is basically the architecture that we will be using, right? We are sampling the current and integrating it over the capacitor here. So if we look at the charge that's being integrated in the capacitor, we can see here the translation of the frequency in this intermediate frequency receiver. If we look here down at the spectrum being converted, we can see here that the signal at the input is well located here, and it is down converted by the mixer, and with the signal processing provided by the discrete-time filters that are typical of this architecture, receiver architecture, right? We have a very nice filtering where we can remove or reduce a lot the impact of the image on this receiver, as well as the other blockers, right? So to understand it better, this architecture, let's take a look at those blocks that we saw on that receiver that are not commonly used in traditional continuous time analog design. So initially, should we sample that in voltage or in current? Actually, when we sample the signal in voltage, we want to hold the switch for a long time so that the voltage of the capacitor is equal to the voltage of the input. Of course, this time depends a little bit on the size of the capacitor, so it's very sensitive to this capacitor sizing. And some of the details that are included in this, some of the issues are variable group delay, clock feed-through, clock jitter. So those are things that are common in voltage sampling. But we want to do a current sampling. So when we have a current sampling, we can see here in phase 1, we close the switch and then we charge this capacitor, but we don't have to establish a level, right? Just during this sample window, we can see that the charge packet that's being acquired. And then we have to reset so that we can sample it again. When we do this process of sampling and reset, we implement a window integrating sampling filter. Well, this also happens in the voltage sampling, but here there is a big advantage because these nodes that are included here, they are used to improve the filtering of the receiver. So going to the sampling mixer, how it works in terms of current, we can see that each time it is sampling the current here, we integrate the charge over the capacitor. And if we use this charge at a different instance here, we can write an equation about this charge being acquired over this capacitor. And again, the window integration sampling filter that I showed before will help to attenuate all the blockers that are coming in the even harmonics for this sampling mixer. So all of them will be attenuated and folded. It is also very interesting. It was shown in 2010 that this passive mixer, this sampling mixer, when we select adequately the switching, here we have a quadrature mixer, differential quadrature mixer. When it is, these phases are well programmed, we have a transparency effect that brings the filtering characteristics of the baseband to the RF input. We can see here below, and basically this translation doesn't change the bandwidth of the filter. So what happens is that we increase a lot the quality factor of the filter. So we can implement this way a very sharp filter in the receiver. Looking at the other blocks of the discrete-time receiver, we can see here the infinite impulse response filter, which is a typically digital block. Actually, it is used in digital signal processing here. But here we are working with discrete-time signal processing. And what happens here is that, again, when phase one is up, let's say, the charge is gone over this capacitor. When we move to phase two, we share the charge between the capacitor CH with capacitor CS, and then we can implement this equation. With this equation, we can also look into the Z transform, and we can see what is the behavior that we achieve, which is a very typical infinite impulse response filter. And we have to look that because of the aliasing, the sampling clocks that happen here at the one sample and 2 and 3 numbers here, we will have folding of these harmonics here, which is a problem because any block, any harmonic that is at the sampling will be directly folded to the baseband and will interfere with our receiver. But if we look at the current implementation of that, we can see that this filtering that is being created by the window integration sampling, right, also attenuates the harmonics. It makes it more friendly to this signal processing that we want to do in the discrete-time receiver. And all these harmonics that are folded, they can bring blockers, but these blockers will be also attenuated with a built-in anti-aliasing effect. Finally, the last block here is the finite impulse response filter, which is very simple. We just have to integrate the charge over this capacitor, and then we move to the next stage, and we will reset in phase 3. When we do that, we implement this nice filter. We also have the window integrated sampling filter here in red, and we will have, of course, some folding here. The number of charge pulses, charge blocks, charge that will be acquiring in this charge packets, actually, we will relate to the number of nodes that we can have on this filter. Going to more advanced blocks, here is the charge sharing bandpass filter, which is the main block that we are using in our receiver. And what happens here is that during this clock samples, we move the charge over the 4 inputs of this filter, right? And when we do that, this charge sharing according to this strategy, we can create a transfer function, which is an infinite impulse response transfer function, but a complex filter, right? If we consider the I input and the Q input here, we have a complex filter. This filter is interesting because the input and the output are coming on the same nodes. The input is in charge and the output is in voltage. With this, we have a very nice transfer function that can be programmed easily just by changing the size of the capacitor CR and CH, or by changing the sampling frequency of this filter. We can also have more complex filters, like this one, where we have 4 inputs and 8 phases. And when we change this, we can improve the selectivity of the filter, and we still can reprogram the frequency if you want. because of this being full rate. I mean, at each time one of these blocks will be sampled, we have a sampling rate of the filter, and we have a null exactly at the folding point, so that we won't have this folding at the receiver, making it good for this RF signal processing. We can also improve this receiver by adding cross-connected buffers here, and with that, and programming this cross-connected buffer, we can even change the selectivity of the filter by a feedback process here. Of course, we need to check the stability analysis of that, because depending on the feedback we have between these two nodes, we can impact the stability of the filter. I need to show this one as well. It's a very nice filter, but we will not go into detail this, because this is not work being implemented in this receivers that I will present. This is an NPF filter, which is provides very sharp filters, and is being widely used in discrete-time signal processing as well. So to summarize this discrete-time receiver characteristics, we have the discrete-time processing in current, and it benefits from the integration sampling. It avoids aliasing, and it can help to attenuate the blocks. We can do a simple analysis with these blocks just by cascading the transfer functions. We will see this in an example right now in the frequency domain. This mixer transparency helps to improve the selectivity, and this is very good because we can sometimes avoid the requirement of front-end filters in this design, right? And these complex bandpass filters are easily programmed. So let's see one implementation of this receiver. It was implemented in 2016, 2017 in 28 nanometers CMOS, bulk CMOS. We can see here actually have the first part of this, which is an RF part. We call it full rate because we are sampling with the same clock of the mixer, right? And then we have a decimated section here that's used mainly to reduce the power consumption of these clock buffers here. The full rate is in charge of the out-of-band filtering, and we need to worry about the anti-aliasing on this receiver. So let's look step by step what happens in this receiver. So in the beginning, we have the LNTA here, and in red and blue here, we have blockers. These blockers can impact the receiver, right? And what the LNTA here, the low noise transconductor amplifier, which is an LNA that delivers current. What it does here is actually to do an initial filtering because it's a narrow band LNA. And this first blocker here, that is 3 times LO, will be attenuated just by the LNA with 28 dB. Because of the signal processing, we will have folding. So all these harmonics will be folded to the LO, the local oscillator, and then we'll translate it by the mixer to the baseband. And you can see here that our signal, that is this shape here, it's lower than the blockers that are coming. So when we add the mixer, this passive mixer with that particular duty cycle clocks that I have shown before. So when we have this passive mixer, it will translate the signal here to the baseband, and will amplify this also because of the LNA. But what happens is that the mixer will also fold this third and fifth order harmonics, and they will appear as well over our receiver. We don't want that, but with the discrete-time filter, we can reduce this impact, actually. If you look here, the shape of this transfer function filter, remember it is an infinite impulse response filter with the harmonics attenuated by the window integration sampling filter, right? So when we do that and we add here, just by cascading the transfer functions, we can see here that the final transfer function here has a very good attenuation of the blockers due to this passive mixer transparency. Also, this filter, which is not very sharp and baseband, when moved to the RF band, can produce a very sharp attenuation, a very high quality factor. So it's interesting to see what happens in simulation. That first block here is here it is actually MATLAB calculation, right? But if we simulate that using cadence and using actually the models of the receiver transistors and capacitors from the PDK, we can see that we have a very, very good agreement with the calculation results by the transfer functions. And we can have here an attenuation of about 60 dB on the third harmonic. The other points here that we see, they are not actually folded to the baseband by the sampling processing, so it's not really an issue. Going to the next stage, which is the full rate session. Remember, we have the first. Actually, we are leaving the full rate section. We are going to the decimated section. So when we do the decimation, what happens is that we will reduce the clock from full rate, which is 9.5 gigahertz. This is the sampling rate according to the size of this pulses here, right? So it's related to the time duration of the mixer itself. So when we go to the next section, we're gonna go to the decimated section, and we have one decimation by 16. So when we implement this decimation by 16, as we saw in the blocks, in the first blocks, the finite impulse response, we implement this filter, right? And here, all this nodes will be translated to the baseband, but they are actually well attenuated already here. And here we can see the transfer function of this block. So when we add this filter, we should remember that this filter is operating at a much lower frequency. It's 16 times lower, actually, with 600 megahertz clock, which is not a big deal for the 28 nanometer implementation that we have, and it can even be low power. So we can see here that we have the shape of this second filter, and we can improve the selectivity here, and the harmonics are coming lower than the 100 dB because of that translation. If we finally include the last filter, this is the full filter stage that we were using, right? We can have here the transfer function of this filter. And since we are using these two blocks with the same clocks, we can see that we don't need to generate the clocks again, and we just need to pay a small price on the buffers for these clocks. If we take a look at the a zoomed version of that curve, we can see here the nice attenuation that we have. So if we're looking here, this is a receiver with 5 megahertz IF. So with 5 megahertz IF, we have here a very nice attenuation. I mean, 15 megahertz off. We already have around 60 dB of attenuation, for instance, here, right? And this is important because after this last filter, we're gonna move to the ADC and convert to the digital signal processing. This was not implemented in this receiver, right? But here we can see the transfer function of the complete filter stage, and then the added signal processing that we have here to achieve the mask that was required by the Bluetooth Low Energy standard. Okay, well, most of what I've shown in the signal processing was actually done in MATLAB with cascaded calculation. So here we can compare in black the MATLAB with these other curves in red, green, and blue, where we have, in fact, the simulated results using PSS, PAC from Cadence. And here we can see that for this mixer, for this receiver here with 5 megahertz IF, we should have like 31 dB of attenuation at the image. Here we have the 5 megahertz. This is a complex frequency spectrum. So we have at 5 megahertz here an attenuation, theoretical attenuation of 31 dB in the MATLAB calculation. But when we have implemented, we see here that we are a little bit off. The standard requires 31 dB, actually, 30 dB of attenuation here. And we are a little bit off. So how can we solve this? This can be easily solved if we change the capacitors. And actually, all these capacitors that were implemented in this receiver were programmable by with binary programmed. So we can see here that just by changing that, we can change and improve the selectivity of the filter, and now achieve the desired performance. Okay, but we're still talking about MATLAB and simulation. So before we go to the measurements, let's just summarize these strategies that we have used, or at least mention some of the points. I have not mentioned that, but because we are working with low power receiver, right? We want to reduce the power consumption. So one of the architectures, one of the ideas that we have is that all the gains in the receiver are implemented with GM and the impedance of the filter. So at each filter stage, we have a transconductor before, which is the LNA, or which is an inverter, and we have an impedance. So if we put a high input impedance on the filters, what happens is that we can reduce the GM for the same level of gain that is required. And this reduces the power consumption of the GM stages. This can be easily done if we change the frequency sampling, or if we just change the capacitor, the rotating capacitor of that filter. And with higher input impedances, we can also use worse switches. Actually, we can use smaller switches with a high resistance, and this will help also to reduce the buffers and the clock generation power. Also, if we reduce the sampling of the receiver, right, and we know that this can reduce the power consumption, we can also increase the output impedance of the filters, and it's good for this power consumption strategy. Another way to reduce this power consumption is to apply a decimation as early as possible. And this comes right at the point we want to discuss at this presentation, which is the aliasing considerations, right? We can reduce the clock power, but we need to work and worry about the aliasing. And because of the lower linearity requirements for IoT, we can also use a moderating version in the design that brings the current down and also the power consumption down. So let's look at some measurement results so that I can show you that this actually works, right? So those are our measurements taken from the BLE in 2017. Here we can see 45 dB of gain for this receiver, and we can see an image rejection of about 45 as well. The linearity of this receiver is very good. It's about minus 17 dBm with a noise figure of 6 dB. Here we have a shape of noise figure and measurement so that we can see. And here we see the transfer function of the filter. So we have here in blue the simulation that we have achieved in the design, and we can see here the measurement so that we see that we have a very good match between the simulated and the results. Also, we have here we measured the Bluetooth standard with Bluetooth packets to check the package error rate, and we have here about minus 95 dBm of sensitivity on this receiver, and with a very good out of band blocking. So in red, in rows here, we can see this masks that were defined by the Bluetooth Low Energy Standard, and we can stand blockers that are much higher than that. Here, just the plots for linearity of this receiver, right? Which is very good. We have 50 dB of IP2 for this receiver. This was implemented together with a transmitter, so it was actually a transceiver, and here we have a switch, integrated switch, so that we can move from the receiver and transmitter with a very good power consumption budget of 2.75 milliwatts at high gain. This was also implemented in a receiver-only design. What we looked at in the receiver, this receiver-only design was we were looking for something to work with smaller voltage, so we put a doubler in front of this receiver, and here we can see what happens when we change the voltage supply on this receiver, right? And we can see how much this voltage supply impacts on the gain of the receiver and the performance of the other blocks here. So we can see that if we increase the supply to 1.1 volts, right, we can achieve the standard that we have seen on the other paper. But if we reduce the supply to 0.55 volts, we can increase just a little bit the noise figure, and the receiver is still working with a very nice IP3. Of course, when we reduce the supply, the IP3 increases. And here we have the power consumption impact of that. Of course, we still maintain the same characteristics of the receiver, which proves that this discrete-time architecture is very good, because it change the supply and still keeps the same filter shape. And of course, with smaller supply, we can stand better the blockers, even than the, with a smaller supply of 0.275. Remember that we have a doubler in front of that, so we can double the frequency, right? So it's actually 0.55 volts at the core. We can still stand the mask. So here we have a comparison of the Bluetooth low energy. It was run with measurement of the packets, actually, to show that it's working. And we have a new sensitivity after reducing the supply of the receiver. Okay, so here we can see what happens with the receiver supply when we change receiver sensitivity, when we change the supply of the receiver, and the impact on the mixer, the image rejection as well. Of course, the image rejection gets worse because the clocks are not so well implemented in the lower supply. This was not planned in the design to improve the clocks, right? And here we have a comparison of the main figures, which are the sensitivity for each one of the cases. And should remember that -70 dBm is the the sensitivity required for Bluetooth low energy. So we're still very well in terms of sensitivity with this receiver. So let's take a look at the aliasing in this discrete time signal processing. We have shown this before during the presentation. Actually, we can see here that if we have the front end, we have the LNA filtering in dashed black. We have the transfer function of the LNA plus filter here in black. And what we need to protect here is that we need to protect the blockers. We have here 68 dB before they will be folded to the baseband. And also, when we look here, after the decimation that we have on this receiver, right, we have all this folding here that will produce aliasing there. And what happens is that if we change the decimation, we can see here the impact. So if we have like 8 decimation by 8 here, we will have an attenuation of the aliasing blockers of 118 dB. But if we use 16, we can stand the blockers of 99 dB off. This is on a theoretical calculation, of course. It reduces a little bit with the implementation, right? We can expect a margin of 5 to 10 dB in the implementation, depending on the quality of the implementation itself. And here, just taking a look at the last stage, we have here in red the ADC, where the ADC signal will be folding, right? We also have folding at the ADC. So we have here this block was using a 20 megahertz receiver ADC, right? So we have the folding here, and since it is a complex ADC, meaning that I have I and Q, and they are all sampling and preserved at the same time. So we have a complex shape. Also, the ADC sampling aliasing points are actually offset one from the other. And of course, if you can change the IF, we're going to see what happens here. And if we move from 4 megahertz, sorry, this was 4 megahertz. If we move from 4 megahertz to 2 megahertz here, we can see that we have an improvement of 10 dB in the aliasing. We reduce the aliasing by 10 dB, and this helps to put this in the ADC to improve the ADC filtering, the anti-aliasing before the ADC, meaning that we don't need actually an anti-aliasing filter before. So here we have a study case to show that. We actually want that receiver that we have implemented, and we want it to be used in a different ADC. We want an 8 megahertz ADC with 9 bits instead of 20 megahertz and 9 bits. So what happens here is that we need to look just at the filtering profile, and then we can see that when we reduce here the IF of the receiver, we have a very nice change here in the sampling, and we can attenuate enough. It is and 9 bits ADC, so we need to go below 55 dB of attenuation for that. Okay, so this is was mainly what I have to show you. Just I have some conclusions before. So Discrete-time offers a new perspective to the front-end design. It's friendly to technology scaling. Is friendly to voltage scaling. You've seen that even in a design, and we can achieve state-of-the-art performance and low power with this. It's also very programmable and can be used also for software-defined radios, for instance. It's important that we pay attention to the aliasing considerations in this discrete-time system-level design. And if we do that, we can even improve the clock and decimation strategies in the receiver and reduce the power consumption on the clock generation, for instance. So before I finish this presentation, I would like to show you what is new in discrete-time receivers. We have this work from 2020, which is a phase tracking receiver from swapping from UCD University. And what happens here is that we have the receiver here at the front, and the signal receiver is also controlling the oscillator and the PLL. So we have a closed loop with the ADPLL to reduce, to improve the performance. And with this, we have achieved 1.5 milliwatts power consumption. Actually, they have achieved it, right? With a very nice sensitivity as well, using a different architecture, like a phase tracking, IF tracking. We also have new strategies on the infinite impulse response filter. So this is very interesting, though a little bit complex switching strategies, but have a very, very nice performance in terms of programmability of the filter, right? So we have a baseband filter, and we can actually program the corner attenuation here. So it is very good for the baseband signal processing. I would like to thank my collaborators on this works, Professor Sérgio Bampi from Federal University of Rio Grande do Sul, Professor Stasevsky from University College Dublin, Dr. Amir Bozorg. We have been working together for quite some time already as well. And my special thanks to Dr. Felipe Baumgratz from Chips Electronics, which is my main partner in this design initiatives. Also, Dr. Feng Wei Ku from TSMC that helped a lot in this chips that I have presented here in all the design and measuring and all the process. I have here some references. I will just go through them so that we can have them recorded, and you can take a look there after if you want. And thank you very much. I hope you have enjoyed the presentation, and I'm open to questions now.
Okay, thank you very much, Sandro Ferreira, for this very nice talk. Congratulations for this excellent work. As you already mentioned, people can look up in the July 2022 issue of TCAS 1, where Sandro's paper in collaboration with URGS and University College Dublin, Professor Stazewski, reviews the advantage of these discrete time architectures in exploring so nicely and wisely the anti-aliasing properties. Now, I have while we wait for questions here, we wait for questions from the audience here. We can type in your YouTube screen questions for Professor Sandro Ferreira. I have one question, okay? The fact that in the latest work that you just reviewed, where you were adapting the LO, you could possibly, with this adaptation, improve sensitivity, or you would prefer to reduce power? And can you show us how the adaptation can reduce power, which is something very, very difficult to grasp? Maybe you can put some lights on how explore this, let's say, adaptability, where you already have the A to D in the loop, and then in the baseband you do some digital processing, and you adapt your LO, because the LO in the end is always controlled by some intelligent processor that adapts, because the LO has to be adapted because of channel requirements. So would you prefer to go for lower power or higher sensitivity?
Okay. Well, that is actually design choice, and that is coming from the product specifications, actually, right? If we want to look more into the power, and we can stand higher, worse sensitivity, let's say. In terms of the design, when we change this sampling clocks, we cannot impact or improve the sensitivity. Actually, we can only make the sensitivity a little bit worse. The sensitivity is only controlled by the gains of the receiver and just the LNTA and the gem cells. We can, of course, add programmability to the LNTA and the gem cells, and we can sometimes increase the gain of these blocks, for instance, the LNA. But we have to look at closely, because if you are doing some decimation to reduce the power, but we still need to increase the power in the LNA, we need to see if that is really helpful, right? So I think that's the main issue. But generally, we can also control that. We can change that during operation. Actually, we can change the clock, for instance, and change the sampling rate during the operation, and we can use that in a like software-defined radio function to improve, reduce the power consumption only when we need, right? And at that moment, maybe we don't need to worry so much about the sensitivity.
Okay. And can you tell us a little bit more about the trade-offs between four ways and 8 phases, and four ways and 4 phases, and with the impact that those choices have on the overall performance?
Yeah, actually,
You can bring back the block diagram to illustrate that from
yeah.
the PDF.
Okay, let me.
Then your answer will be much more. Will be easier to assimilate by the others.
Okay, so here. So let me see if I can show it better with the block diagrams here. So one thing that we can do actually is if we improve the selectivity of the filter, for instance, if we improve the selectivity of the filter, we can maybe use only 2 stages instead of 3, and then we also reduce the power consumption. I didn't put it clearly, but the power consumption on the discrete-time filters is coming from the clock generation. So if we have less filters, then we can reduce the power consumption. If we improve the selectivity, we can reduce the number of filters. And also, if you pay attention to the decimation, we can decimate even further and reduce the power consumption because of that. Maybe with more phases, we can increase the selectivity of the filters and use only 2 stages. So there are many trade-offs in this. This is something that can be thought up front. The good thing is that the design of the filters is very easy. So once you select the correct size of the capacitors and the sampling frequency, is basically layout. You don't have to do anything else.
Okay. And one other question is, can you tell us about when you do the boosting of the selectivity by putting the positive feedback? I think you have further down some slides where you bring that. How much that positive feedback compromises in terms of increasing the power consumption of the overall? Was it a small increment? And I know Felipe Baumgartz in his PhD thesis he's done in our group. He looked into that GM boosting. But how much power did we compromise with that solution?
Sure. Let me see if I can move quickly to this one.
I think it's further down the slide deck.
Yeah. There's a lot of animation, so it takes a little bit longer to do that. Oh, here we have it. Yeah. Okay. So actually, the main thing here is that well, the power consumption doesn't increase so much because we are using basically inverters here, right? And actually the signal that is coming here doesn't have a big amplitude. These inverters are working as amplifiers, so the impact in the power consumption with this is not very big, and it's very good that we can see here that we can improve a lot the selectivity, and in this sense, we may even be able to try to find one strategy with this feedbacks here, so that we can maybe use only 1 stage, and in this way reduce even further the power consumption.
Okay. Yeah, you see here an 8 clock phase that was published by Felipe Baumgartz, who is now at Chipus Microelectronics, a designer in that group. He published in TCAS 1 2020. In his PhD thesis, he included this boosting, and Sandro and Felipe have improved a lot these filters, the bandpass filters for applying in this discrete receiver. We have a question here from the audience in the YouTube. Altamiro Suzin, hello Altamiro, hello Suzin, very nice to see you. So he congratulates for these nice results that you have, but what do you plan to be the next steps in terms of next silicon tape outs that you have? By the way, we have done tape outs every year in some RF or energy harvesting blocks with Sandro, with collaborations with some groups abroad, like University College Dublin in Ireland. So comment.
Yeah,
The last question. What is next, and then we close for the day.
yeah, we actually have some designs cooking. We should have soon some new approach to these receivers, right? We are actually measuring that, and measurements
Currently
have
measuring.
also,
Currently
yeah, with
measuring.
this collaboration with UCD. So we have a new designs also with this feedback programmability, for instance, and some other approaches. So we should see that soon. What's the next steps when I look into silicon? Well, if you look at the first part that I mentioned, we are at this moment after this paper. These papers were produced in 2018, so we are a little bit far from the state of the art at this moment. So the next step actually is to try to get back on track. And the best receiver at this moment has a power consumption of about 400 micro
Microwatts.
watts. And we are with the last design at 1 milliwatt. So it's easy to get below 1 milliwatt, but to get to 400 microwatts is not so easy. So that's the next target.
Target. Okay, yeah. Well, we all know, you and the audience know, and you're talking about a Bluetooth low energy receiver, which have billions of devices per year. So we're talking about a high volume
Yeah.
product in which every 20 microwatts of reduction makes an impact in getting part of the market of a billion. That's why TSMC is a partner on taping out and fabricating those designs by Sandro, just because they are interested in this big volume market, and that's BLE is a very hot topic. BLE transceiver receiver especially, which sells billions and billions more. Okay, we no more questions here in the audience. No more, no more questions in the Cyberland. So thank you very much. Hello, Artur Livaneto. Good to see you also. He's part of the group. So I would like to congratulate Sandro for his excellent presentation and reviewing this very important subject. If you want to delve more into those subjects, look at the reference that he has shown here at the end of this presentation. Many papers are done by authored by Sandro and Felipe Baumgratz in our university here in Porto Alegre, in collaboration with groups abroad. So please stay in touch and send a note to Sandro whenever you are more interested in trying to understand this nice and very state-of-the-art architectures for receivers. Thanks a lot, Sandro. Your last words?
Well, this Bluetooth Low Energy, as you mentioned, is top in terms of marketing for market of IoT. So there is a very strong research in that, and we are trying to improve every time it even more, right? And if you want to know more or start using discrete-time receivers or understand it a little bit better, you can look at the papers that I have provided, or you can just reach out and we can have some chat and maybe have a coffee and we can discuss that. Thank you very much for
we thank you.
the attention.
Thank you very much, Sandro. Bye-bye.
So thank you very much, Sandro, for the very nice talk. Thank you, Bumpy, for sharing the session. So have a nice weekend and see you next Friday. Bye-bye.